Okay, students, welcome back to the second part of a two-part lecture on probability distributions. We're going to learn about three continuous probability distributions: the uniform probability distribution, the normal probability distribution, and the exponential probability distributions. Let's start. Okay, let's go over the learning objectives for this chapter. The first one is to describe the uniform probability distribution and use it to calculate probabilities. Second, to describe the characteristics of a normal probability distribution. Third is to describe the standard normal probability distribution and use it to calculate probabilities. Lastly, we're going to describe the exponential probability distribution and use it to calculate probabilities. Okay, so let's start with the simplest continuous probability distribution, which is the uniform distribution. Okay, so the uniform distribution characteristics are the following. First, it is rectangular in shape. Second, the mean and the median are equal. And third, it is completely described by its minimum value A to the left and then the maximum value B to the right. Okay, now if we know the minimum and the maximum values, then we can calculate the mean, the variance, and of course the standard deviation, and any probability that you wish to find. And so if you look at the picture, then you can see the rectangular shape of the uniform distribution with a minimum value of A and a maximum value of B. It's called the uniform distribution because the probability of a particular outcome in this distribution is 1 over B minus A. So the mean and the standard deviations are the following. So the mean itself is going to be A plus B divided by 2, whereas the standard deviation is going to be the square root of the difference between B and A divided by 12. Now, the following equation describes the region from A to B, or basically this is the definition of uniform distribution. So the probability of x is equal to 1 over B minus A if x is between A and B inclusive and 0 elsewhere. So this is the definition of a uniform distribution. So again, you have to note that the definition includes P of x equal to 1 over B minus A if x is included between A and B inclusive, and the probability of x is 0 elsewhere. Okay, so let's take an example. So Southwest Arizona State University provides bus service to students while they are on campus. A bus arrives at the North Main Street and College Drive to stop every 30 minutes between 6 a.m. and 11 p.m. during weekdays. Students arrive at the bus stop at random times. The time that a student waits is uniformly distributed from 0 to 30 minutes. And so in this particular case, A is going to be 0 and B is going to be 30. And so the height is going to be 1 over B minus A, which is 1 over 30. And so it's going to be 0.033. Okay. Now, the area of the uniform itself is going to be 30 minus 0, which is equal to 1. And then the mean itself is going to be A plus B divided by 2. In this particular case, it's going to be 15. The standard deviation is the square root of the square difference between B and A divided by 12. And the standard deviation is going to be 8.66. So basically, the typical wait time for bus service is 15 minutes, and the variation in student wait times as measured by the standard deviation is 8.66 minutes. Now, we can also look at a specific probability. In this particular case, we're interested in looking at the probability that student will wait more than 25 minutes. And so recall that the waiting time is always between 0 and 30. And so the probability of waiting time between waiting more than 25 minutes is going to be the probability of wait time between 25 and 30. And so is just going to be the height multiplied by the base. And so basically the height is going to be 5 divided by the base, which is going to be 30. In this case, the probability that student will wait more than 25 minutes is going to be 0.1667. What about the probability that a student will wait between 10 and 20 minutes? Well, basically what you need to do is just calculate the area. So basically the area is just 20 minus 10, which is 10, divided by 30, which is the overall area. And so basically the probability that a student will wait between 10 and 20 minutes is going to be 0.333. Okay, so the normal probability distribution is a continuous distribution with the following characteristics. It is bell-shaped and has a single peak at the center of the distribution. The distribution itself is symmetric. It is asymptotic, meaning that the curve approaches but never touches the x-axis. It is completely described by its mean and standard deviation. So there is a family of normal probability distributions. Another normal probability distribution is created when either the mean or the standard deviation changes. So basically we can have an array of normal probability distributions depending on the mean and the standard deviation or the variation or the variance. And so this is a depiction of a normal probability distribution. So it is symmetrical, two halves identical, and you have tail on both sides of the probability distribution. So theoretically the curve extends to positive infinity and negative infinity. So the mean, median, and mode are equal. Okay, so the dispersion or spread of the distribution is going to be determined by the standard deviation. So we can see in the subsequent slide, the larger the deviation, then the larger the depiction of the bell curve itself. The distribution or the location of the normal distribution is going to be determined by the mean. So you can have either a positive or larger value of mean, or negative or a lower value of mean. Now the area below the curve, so the area below the green curve is defines the probabilities, and the total area under the curve is going to be 1. Okay, and so since the total area of the curve or the total probability is equal to 1 and it is symmetrical, then the area to the left of the mean is 0.5 and the area to the right is 0.5. And so if you fill in the shade on the right half of the curve, then the area is going to be 0.5 by definition. Okay, so again, there is not just one normal probability distribution, but a family of them. Okay, and so in the top left chart of length of employee service at 3 different plants, so the mean is the same. However, you can see that the standard deviations or the variance are different. Okay, so in this particular case, the lower the variance, then the closer the distribution is to the center of the distribution or to the mean. However, the larger the variance, the spread is going to get larger. Okay, so in the bottom chart of box weights of 3 different cereals, the means are different, but the standard deviations are actually identical. And in the top right of the tensile strength of 3 different cables, we can see that they have different means and they also have different standard deviations. And so, for example, the probability distribution with the green line has the middle mean. However, it has the largest variance. The one with the orange line has the highest mean, but at the same time, it has the smallest variance. And so basically, these are the families of normal probability distribution, which is dependent on the mean as well as the variance. Okay, so the standard normal probability distribution is a particular normal distribution. Again, we can have a family of normal probability distribution, a standard normal probability distribution has a mean of 0 and a standard deviation of 1. Okay, now we're going to use the term z-value, which is the sign distance between a selected value designated x and the mean mu divided by the standard deviation sigma. So any normal probability distribution can always be converted back to a standard normal probability distribution with the following formula. So the value of z is going to be the value of the selected value of x, excuse me, minus the mean, mu, divided by the standard deviation, sigma. Okay, so this is called the z-value or the z-scores. So for example, if you have a normal probability distribution with a mean of 40 and a standard deviation of 50, you can always calculate the value of x for that probability distribution and then get the z-value or the z-score. Now, in your textbook, you can actually now look at what's called the z-table. You can also find it easily in Google by typing the standard normal table or the z-table. And so basically on the rows you have the value of z. So this is like the value, the first values of the z. It could be 1.3, 1.4, and so on. And on the columns you can have the extension of the value in the rows. So for example, you can have the value 1.30. You can have the value of 1.31, and in that case the z-score is going to be 0.4049. You can also have the z-score for 1.53. In that case it's 0.370. Okay, now this z-table is going to be particularly handy when we're going to calculate the probability of a particular problem. Okay, now let's take a look at an example. So ride-share services are available internationally. A customer uses a smartphone app to request a ride. So then a ride driver receives the request, picks up the customer, and takes the customer to the desired location. No cash is involved. The payment for transaction, all is handled digitally. So suppose that the weekly income of rideshare drivers follows the normal probability distributions with a mean of 1,000 and a standard deviation of 100. What is the z-value of income for a driver who earns 1,000 and 100 per week, and for a driver who earns $900 per week? Okay, so let's gather the information that we need to calculate the z-scores. So the first one is the mean. The mean is quite straightforward of 1,000, and the standard deviation is $100. And so basically, if we want to calculate the z-value for a driver who earns 1,100, it's just going to be 1,100 minus 1,000 divided by 100. So the z-score is going to be 1. And the z-value or the z-score of a driver who earns 900 is going to be 900 minus 1,000 divided by 100, which is -1. Okay, and so regardless of whether z is plus or -1, then the area under the curve is always going to be 0.3413. What's the reason? It's because that it's symmetrical. So the area to the right is going to be equal to the area on the left, and so the absolute value of the z-score, or the area of the curve for the absolute value of z is always going to be similar. Now we can also recall back the empirical rule. This is something that we've seen in the previous chapter, particularly in chapter 3. So basically we can find a z of 1. This corresponds to 0.3413. So plus minus 1 standard deviation is going to be 0.3413 multiplied by 2, which is 0.826, which is approximately 68% of the observations. A z of 2 corresponds to 0.4772. So plus minus 2 standard deviations is going to be 0.4772 multiplied by 2, which is 0.944, or about 95%. And a z of 3 corresponds to 0.4987. So plus and minus 3 standard deviations equals to 0.4987 multiplied by 2, which is 0.9974, or practically all at about 99.7%. So this is something that we've seen before, and this is a handy application of z-score to verify the empirical rule. Okay, so if the distribution is normal and you know its mean and standard deviation, then you can use the empirical rule to find probabilities of plus n or minus 1, 2, or 3 standard deviations. Now, as part of its quality assurance program, the Autolite battery company conducts tests on battery life. For a particular D-cell alkaline battery, the mean life is 19 hours. The useful life of the battery follows a normal distribution with a standard deviation of 1.2 hours. And so in this particular case, the mean is 19 hours and the standard deviation is 1.2 hours. Now, about 68% of the batteries failed between what two values? Well, basically it's going to fall between plus minus 1 standard deviation. So it's going to be 19 plus minus 1 multiplied by 1.2 hours, which is between 17.8 and 20.2 hours. Now, what about 95% of the batteries failed between what two values? Well, it's basically 19 plus minus 2 times the standard deviation. Where do we get the 19 plus minus 2 times 1.2? Well, it's actually from the empirical rule. So 95% of the distribution is going to fall within 19 plus minus 2 standard deviation. And so basically in this particular case, 95% of batteries will fall between 16.6 and 21.4 hours. You can verify independently for the third one, which is all batteries failed between what two values. Okay. Now, let's get on to the subsequent slides, more challenging ones. In this particular case, we're going to find areas under the normal curve, which is the probabilities of an observation or an outcome is between two particular values. Okay, so we've established that the z value of income for a driver who earns 1,100 is going to be a z-score of 1. Okay, now you can take a look into the z table and you can find that the z-score of 1.00 is going to be 0.3413. And so basically what you're going to do is you're going to depict a normal distribution graph and you start from the mean. Again, since this is a standard normal distribution, then what we can do is that we can show that 0 is the mean in the middle. And then there is a value of 1, which is the z-score of a 1,100 wage, and it is going to be to the right of the mean of 0. And so basically what we're interested in, what is the area under the curve between 0 and 1. 0 corresponds to the value of the mean of 1,000, and then 1 corresponds to the driver wage of or salary of 1,100. Okay, so basically the probability that the weekly income of Uber drivers is between 1,000 and 1,100 is going to be 0.313. Now you can also ask, what about the probability of weekly income below 1,100? So basically it's going to be between 1 to negative infinity. Now we discussed in the previous slides that the area to the left of the mean is going to be 0.5 of 50%. Okay, so basically the area to the left is going to be 0.5, and the area to the right until z-score is equal to 1 is 0.313. So basically the probability of weekly income below 1,100 is going to be 0.8413. Quite straightforward, isn't it? Okay, now the next question is, what about the z value of income for a driver who earns 790? So in this particular case, the z-score is going to be x minus mu divided by sigma, which is 790 minus 1,000 divided by 100, which is negative 2.1. You can go to the z table, and first you have to recall that the z value the absolute z value is going to be the same. So irrespective if on the right, or plus 2.1, or to the left, negative 2.1, the probability or the area under the curve is going to be similar. Okay, so basically for a z-score of negative 2,110, then the probability of the shaded area and from 0 until negative 2.1 is going to be 0.4821. Now, we're interested in two probability values depending on the question. So the first one is, what's the probability that the weekly income is between 790 and 1,000? The probability is just the orange shaded area, which is 0.4821. But you may also be interested what happens if what's the probability of a really bad day or like a really bad week and obtaining income below 790. Well, in this particular case, you can just recall that the area to the left, so basically from the mean to the negative infinity, is going to be 0.50, and so the area to the left minus the area shaded with orange is going to be 0.5 minus 0.4821, which is 0.079. And so the probability that a driver earns below 790 is going to be 1.79%, which is quite low given the distribution. Now, another one which is relatively more tricky, but again, this is something that we can definitely look. And so we're going to combine two areas or probabilities under the curve. One area to the right of the mean, the other area is to the left of the mean. Now, to find the area between 2 points on different sides of the means, we're going to determine the z values for the right-hand side of the mean and to the left-hand side of the mean, and then we're going to add the corresponding probabilities. And so in this particular case, we're going to start with driver who earns specifically $840. In this particular case, the z-score is going to be 840 minus 1,000 divided by 100 is negative 1.6. The z value of income for a driver who earns 1,200 is going to be 1,200 minus 1,000 divided by 100, which is equal to 2. So the first one is, let's calculate the probability that the weekly income is between 840 and 1,000. In this particular case is 0.4452. The probability of weekly income between 1,000 and 1,200 is going to be 0.4772. And so now you can actually combine the area of the two probabilities. So the probability of income between 840 and 1,200 is going to be 0.4452 plus 0.4772, which is 0.9224. So the probability of weekly income between 840 and 1,200 is going to be 92.24%. Now, this is going to be the trickiest of all. Why? Because you're actually going to find area within either side of the probability distribution. It could be on the right, it could be on the left. But in this particular case, it's going to be quite challenging because we're not looking at the area until the negative infinity, but it's actually an area until some point to the right of the value of interest. And so in this particular case, we're interested in looking at the probability of weekly income between 1,000, 150, and 1,250. Now, the first thing to do is actually to find the z-scores. So the z-scores for a driver who earns 1,250 is going to be 250, and the z-value of income for a driver who earns 1,150 is going to be 1.50. Okay, and so let's look into the z-table and find the probability of weekly income between 1,000 and 1,150. And you can see from the table it's going to be 0.4938, and for the probability of income between 1,000 and 1,150 is going to be 0.4332. So basically the probability of income between 1,000 and 150 and 1,000 and 250 is just going to be the difference between the two probabilities. In this case, the difference in probability is 0.606. Okay, so given that, we can now calculate the probability of earnings between 1,150 and 1,250, and in that particular case, it's about 6%. Okay, let's put this into a practical example. Leighton Tire and Rubber Company wishes to set a minimum mileage guarantee on its new MX100 tire. Tests reveal the mean mileage is 67,900 with a standard deviation of 2,050 miles. And the distribution follows a normal distribution, and let X represent the minimum guaranteed mileage and use the formula for Z to solve so that no more than 4% of the tires needs to be replaced. And so basically what we can do is we're first going to calculate the z-score, and then from the z-score then we can now calculate the mileage. Okay, so now what we can do is we're going to identify the fact that the z formula, so that no more than 4% of tires needs to be replaced. And so in this particular case, 4%, it's about 0.04. And so the idea is, what's the value of X such that the Z is going to be 0.04. So let's find first the shaded area. So again, the shaded area is going to be 0.50. It's going to be 0.04. And so what is the probability of value between the mean and X, the value of interest? So it's going to be 0.5 minus 0.04. And so it's going to be 0.46. And so if you look at the table, then the closest value to 0.46 is going to be 1.75. It's actually negative 1.75. And so you can use the z-score formula. So it's going to be minus 1.75 is going to be equal to X minus 67,900 divided by 2,050. Now from there you can find that the X is actually 65,312 miles. And so basically the minimum guaranteed mileage should be set at 64,392 miles, so that 4% of the tires will be replaced under this plan. Okay, now the good thing about the normal distribution is that it could be used to approximate other distribution, and in particular it's going to be useful in approximating a binomial distribution. So the normal distribution can approximate under certain conditions. First, the value of n multiplied by the probability of success, and n minus the pi, which is n minus the probability of success, must both be at least 5. Okay, so this is something that you need to remember. N is the number of observations, and pi is the probability of success. So there are 4 conditions for binomial probability distribution. This is something that we've seen in the previous chapter of chapter 6. First, there are only two possible outcomes, and then you're going to classify that as either a success or a failure. Pi remains the same for trial to trial, and the trials are independent. And lastly, the distribution results from a count of the number of successes in a fixed number of trials. Now, in this particular case, we can use the normal distribution as a substitute of binomial distribution for large values of n. Why? Because as n increases, a binomial gets closer and closer to a normal distribution. Okay, we'll see this in subsequent chapters, but this is a good thing to know now. Okay. So the last continuous probability distribution that we're going to discuss today is the exponential probability distribution. So the exponential probability distribution describes times between events in a sequence. The actions occur independently at a constant rate per unit of time or length. It is non-negative, is positively skewed, declines steadily to the right, and is asymptotic. Examples of situations using the exponential distributions include the service time for customers at the information desk at Dallas Public Library, the time until the next phone call arrives in a customer service center. Now, this is the depiction of family of exponential distributions, and the value is going to be dependent on the parameter lambda. Lambda itself is going to be referred to as the rate parameter. Okay, so the graph starts at the value of when the random variable x value is 0, and then it's going to decline steadily as we move right with increasing values of x. Now compare the shapes of the different exponential distributions as it changes from a third to 1 to 2. Okay, so the one with a rate parameter of a third is going to be depicted with the blue line. The one with a rate parameter of 1 is going to be depicted by the orange line. And then the rate parameter with lambda equals to 2 is going to be depicted by the green line. Okay, so for the exponential distribution, the probability of x is going to be lambda multiplied by e to the power of negative lambda x. So the area under the curve is given by the following formula. So the probability of arrival time less than x is going to be 1 minus e to the power of negative lambda x. Okay? All right, so let's take a look. The orders of the prescriptions arrive at a pharmacy website according to an exponential probability distribution at a mean of 1 every 20 seconds. So basically here the rate parameter is going to be lambda equals to 1 over 20 or 1/20th. Now find the probability that the next order arrives in less than 5 seconds. So here x is equal to 5. So the probability of arrival time less than 5 is going to be equal to 1 minus e to the power of negative lambda times 5. So in this particular case it's going to be 1 minus 0.7788, which is equal to 0.2212. So there is a 22% chance the next order will arrive in less than 5 seconds. Okay, and if we see this, this is in the left tail area of the exponential distribution. Now we can also ask what's the probability that the arrival time is going to be higher than 40 seconds or more than 40 seconds. And so in this particular case, we're going to find the probabilities that the next order arrives is more than 40 seconds. Now in this particular case, it's going to be the probability of arrival time more than 40, which is going to be e to the power of negative lambda, which is 1 over 20th times x, which is 40. This case is going to be 1.1353. And so in this particular case, the likelihood or the probability that it will be more than 40 seconds before the next order arrives is going to be 13.5%. So this is the end of chapter 7. Thank you for listening. I'll see you in the class. Thank you.